Welcome to the second part of exponential functions. We are going to be talking about that idea called compound interest. Compound interest. Compound interest. Compound interest. Compound interest was the idea that you're going to let your money build throughout different portions of the year, as opposed to just simply at the very end of the year. Let me show you what I mean. You have $9,000, let's say, to invest in a savings account that gives a 1.02% interest rate annually. So at the end of the year, you're going to get that interest rate, but your money will not just grow at the end of the year. The bank is going to let your money grow throughout 4 times out of the year. So that's called compounding quarterly. So this interest rate is going to be compounded quarterly. The question is, how much money will you have after 3 years? It turns out we can still use kind of the basic idea of all exponential functions. So we have an initial value, a, and then the b value is our growth factor. So we can kind of manipulate this to fit this example. That's what I mean. The initial value here is going to be $9,000. And every year we're going to multiply by a particular growth rate. So we're always going to have the $9,000. So we talked about that previously. That one represents all those $9,000. And we're going to add this expression. So we have the interest rate written as a decimal, and we're going to divide that into 4. So the reason for doing this was that the bank is going to give you this interest rate 4 times throughout the year. So you'll get a quarter, and a quarter, quarter, and a quarter. In total, you're going to end up with that interest rate. But you're going to let your money build 4 times throughout the year. This lets your throughout the year. Okay, so you're going to get this interest rate 1, 2, 3, 4 times. So instead of letting your money build at the end of the year, it's going to let your money build 4 times throughout the year. Even though your interest is going to be a little bit less, it turns out you make a little bit more money. So if it's happening 4 times throughout the year, our exponent on this expression is not going to just be 3. It's going to be 3 times 4. Because if it's building 4 times throughout the year, so each time this interest rate will be cut into fourths, but it's going to happen 4 times every year. And after 4 times for every 3 years, well, that's going to be 12. So if we evaluate this expression, it turns out that we get this solution. So our bank account would be worth $9,279.30. And so we made $279. Just to convince you that we actually are getting a little bit more money, check this out. This is compounded annually. So the expression would just be 9,000 times 1.0102. And let's just see how much money we'd have after 1 year. So if we compounded it annually, we'd only compound the money 1 time throughout the year. And this interest rate wouldn't be divided into 4 pieces or 12 pieces. We would just get the interest rate, and that's it. So this approximately equals $9,091.80. Okay, so we made $91 that year if it was just compounded annually. However, let's check if it was compounded quarterly. I guess I shouldn't say 1 time, I should say after one year. So if it was compounded quarterly after 1 year, it would be 9,000. 1 plus 0.0102 divided by 4, because we're going to get a quarter of that interest rate, but we're going to get it 4 times throughout the year. And this equals approximately 9,090. You guessed it, too. We make a little bit more money, just a touch. We make, it looks like 35 extra cents. 35 extra cents. Whoa! That's great. That's like what, 35 cents? Look at you borrowed 35 cents. You could buy a banana, maybe a really cheap apple. But remember Avi's rule? Remember Avi's rule from class? We noticed that Avi's rule took a while, and then eventually it started to really increase. So exponentials have that behavior. So right now, 35 cents really, it's kind of like here. We don't, but this is like 1 year. Over here would be like, so at year 12, you're probably going to be making a lot more money than just 1. So you got to be patient. Like a doctor, you have to have a lot of patience. I have some exercises for you. You can tell because it says exercises right here. And here's the first one. So based off the first video, go ahead and check out that first video. you're going to write the exponential model with the given initial value and growth rate. So, if you don't know what an exponential model is, be sure to look at that very first video. Initial value for the first one of 5 with a growth rate of 1.23%, and for the second one, an initial value of 1/4 with a decay rate of 53%. This next one, I'd like you to write an expression that would help you find the ending balance of a savings account that compounds the interest monthly after 10 years. The initial amount in this case is $10,000 and the interest rate is 0.53%. So for those of you looking to reassess or some practice problems, these are some good ones to consider. Here's the thinker that I will leave you with. This particular example, it's the same exact problem here, but what if it wasn't compounded every month? What would happen if you compounded that interest rate every second throughout those 10 years? How much money would you have? $1 million? $1 billion? $1 trillion? Figure it out. Thanks for watching. I will see you in the classroom. I'm going to make a little bit of a cup of coffee, cup of joe. Here's your cup of joe. Boom, boom.